Okay, so let's go now to the case that we usually have when we analyze microarray data. And this case is when we want to explain the expression values of the genes, but when the explanatory variables now are discrete, not continuous. So in the previous video we saw a continuous example, and this was the age. The age is a continuous random variable. And now, usually, in microarrays we have discrete explanatory variables. This is because usually in microarrays we deal with two conditions. For example, we try to find genes that are differentially expressed between healthy or sick people, between people that get some drug and people that do not get the drug, between people who smoke and between people who do not smoke, and so on. So in most of the cases we have to explain the expression level of genes with some discrete explanatory variables. Now these discrete explanatory variables, usually we call them factors. So often you will have the term factor, and by this you will understand that this variable is a discrete one. And we will deal with two cases. The first case is when is the so-called means model. So in the means model we try to explain the expression level using this writing here. So the expression level can be modeled. Now if the explanatory variable, okay, let's go from the beginning. The explanatory variable x is the factor that we are interested in, and this might be the health condition. So if we talk about the health condition, this health condition might have two levels: the level 1, which is healthy, and the level 2, which is sick. Now this x is a factor, is a discrete variable with two levels here, and we try to explain the expression level based on the values of these two factors, of the values of these two levels of this factor. And the way that we model it with linear models is like that. Again, I have to say that this is the means model because later on we will see another way to write this equation here. Okay, so the expression level depends on the level, on the value of these two levels here. Okay, so if an individual is healthy, then this individual will have 1 for the value x1 and 0 for the value x2. So an individual that actually has this x1 level, it will have 1 for this level and 0 for the other level. This is the way that we parameterize this. And vice versa, if the individual is sick, then, okay, let's write this correctly here, then this individual will have 0 for the x1 level and 1 for the x2 level. So for example, if we have 3 individuals and these individuals are sick, healthy, then the values of x1 and x2 for these 3 individuals will be, for the first one it will be x1 0 and x2 1, second one the same, x1 0 and x2 1, and the third one it will be x1 1 and x2 0. Now with this way we can say that the expression level, for example, for the healthy individuals, the expression level will be B1 multiplied by 1 plus B2 multiplied by 0, so this will be B1. So what the model predicts is that for the healthy individuals, the expression value must be around B1. Okay, let me correct this one here, it's typo. Okay, so for the healthy individuals, the ones that belongs to X1 category, the expression, our prediction for the expression value is actually around these points, and it's B1 here. It's the mean value of all these values that healthy individuals have. And for the sick individuals, the expression will be B1 multiplied by 0 plus B2 multiplied by 1, and this will be B2. So this, the model predicts that for the sick individuals, the expression values must be around B2. So B2 is here, and these are the values that we have. Okay, so in fact what the linear model predicts is the mean expression values for the healthy and the sick individuals. And for the healthy individuals, the prediction is B1, it's the coefficient of this X1 here, and for the sick individuals, the prediction is B2, and B2 is here, and it's the coefficient of this X2 level here. Okay, now usually we are not interested in this B1 and B2 per se, because we really don't care what is the mean expression value of the healthy and the mean expression value of the sick, but we care if these mean expression values are different. So we really care about this height here, this difference here. So we care about the B2 minus B1. And when we apply statistical test using these points here, we have the null hypothesis that this difference, let's call it delta. So the null hypothesis, the H0 for this one is that the delta equals to 0. And the H1 is that delta is different than 0. So using these values and this null hypothesis and this alternative hypothesis, we will test whether this difference is or is not 0, statistically speaking. Okay, so we can see now some example. Okay, so let's see the following example. Let's assume that we have a gene. Let's suppose that this is the gene 1, and for 4 healthy individuals, the expression values are the ones that you see here. So 2.4 for the first healthy person, 7 for the second healthy person, and so on. And we also have 4 sick individuals, and these are the expression values. Now, we don't there is no need to be 4 individuals and 4 individuals. The number might be different, but let's suppose that these are the data that we have. So this data could be, for example, one row from the expression matrix. So if this is the expression matrix, where here we have genes and here we have individuals, samples, then we will have 8 samples in total, 4 healthy and 4 sick, and for example this row here will be the expression of gene 1, So 4 values here and 4 values here, and these are the 8 values in total. Now totally the expression level, so the whole row, will be when we concatenate the healthy and the sick individual. Okay, the expression obviously is this vector. Then what we do is that we create a factor vector, so a vector of factors for the condition of each individual. And we have 4 healthy and 4 sick. So we set the level of healthy to 0 and the level of sick to 1. So 4 zeros and 4 ones, and we assign to 0 the healthy and to 1 the sick value. So if we run this command, we have that the levels are healthy, 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 and sick, 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 sick. And the first level is the level 0, and then is the level 1. If I would put this vice versa here, I assume, but I'm not sure, that the vector would be opposite. First will be the sick, and then will be the healthy. So it doesn't really matter here so much. I will just put 0 and 1. But remember that when we will have the means reference model later on, the 0 level will be the basic level. Okay, and now the expression value can be modeled using a linear model here as a function, we use this tilde, of the condition. And since we talk about means model, we have to put this plus 0 here. If we don't put this plus 0, then R will try to explain, will put the 0 level here as a basic level, and then we'll try to explain the level 1 as a difference from the basic level. You will see the difference later on in the next video. So I run this command, and then in order to see the results, I use the summary of my model. And we have the following thing. So the result is this table down here with the coefficients. So these coefficients here are the B1 and the B2 values. And it says that for the healthy individual, so if I remember well, for us it was this B1, the estimation is 3.7 from the data, and the p-value assigned to this is 0.17. And for the condition sick, the sick level, the estimation is 16.87.5, and the p-value assigned to that is the 0.000406. So these two p-values do not say if health is different than sick. It tells us if the B1 here and the B2 are statistically different than 0. So the healthy one, so this level here, B1, is not statistically different than 0 because the p-value is 0.17, but this one is statistically different than 0 because the p-value is 0.00406. So this means model actually does not tell us if healthy are different than sick regarding the expression value, it tells us just if these estimations here are statistically different than 0. Now, what are these estimations? In fact, is the mean value of the healthy people and the mean value of the sick people respectively. So for example, if I will just calculate the mean value of these expression levels, it's 3.7. You see it's exactly the same like this one. And the mean value of the sick people is 16.875. It's exactly the same as this value here. Okay, maybe you ask, okay, why to do all that since we can just calculate the mean values? And the answer is because all this process provides us also the p-value if these estimates are statistically different than 0. However, with the means model, at least using the LM function, we don't get the result whether these two values are statistically different from each other. And this is what we are interested in. In the means reference model, we'll actually get this result immediately. Okay, in the next video we will see the means reference model then.